welcome to the Peak Electronics booth at Electronica in Munich. Peak Electronics is one of the leading manufacturers of DC-DC converters with a wide range of more than 20,000 standard types. In addition to the standard types, Peak offers custom-designed products. This comprehensive range of products is supplemented by high-performance AC-DC converters, DIN rail modules, customer-specific power supply units, switching regulators and LED drivers. This video is about selecting a DC-DC converter. In few steps we explain the most important criteria to select the converter optimized on the application needs. When do I use a DC-DC converter?
A DC-DC converter is generally used if the supply voltage available is not compatible with the input voltage rating of the electronic application. The optimum selection of a DC-DC converter is often not as simple as you might imagine, since it is not solely a matter of determining input voltage, output voltage and power. The following is an overview of the most important criteria to consider when selecting and applying DC-DC converters.
Let's start with one of the most important things, the output voltage.
In most applications, it is known what voltage needs to be supplied to an electronic device. However, there are also devices that can be operated over a wide input voltage range. For example, from 8 volt to 15 volt. Alright, so what now? These devices often integrate a linear voltage regulator that generates a regulated lower voltage from a higher voltage. For example, if we are talking about a 5 volt regulator, this then means that the linear voltage regulator burns the voltage difference to the output voltage of 5 volt. That is, turns it into heat. The current remains almost unchanged. Hence, the higher the input voltage, the greater the resulting amount of heat. That is, power loss. In this example, it is recommended to choose a DC-DC converter with an output voltage at the lower range of the possible 8 volt to 15 volt. For an application where small quantities are involved, a DC-DC converter with the nearest standard output voltage would be used. This would be a converter with an output voltage of 9 volts. By contrast, for applications where high quantities are involved, it makes more sense to choose a converter with a special output voltage of 8 volts. This is because the higher the power loss, the more complex the thermal management in an overall system becomes. Moreover, the DC-DC converter must first of all produce the power that is then subsequently burnt as heat. A DC-DC converter with an 8 volt output voltage, as in this example, must only deliver just over half of the power compared to that of a converter with a 15 volt output voltage, and is thus more compact and significantly more cost-effective. As a rule, it makes sense to test the device, for example with a laboratory power unit, to observe the behavior of the current consumption. Also, under various operating conditions, as well as operational safety, under consideration of the applied voltage in order to determine the output voltage of a DC-DC converter.
Important features are also the output current and the power. How can the DC-DC converter power be determined?
3 operating conditions of the device being supplied should be considered when determining the performance of the DC-DC converter. Startup behavior, nominal operating condition, and operating condition with maximum energy consumption. The critical part is the startup behavior. When switched on, a lot of devices draw a high startup current for a short period of time that is caused, for example, by capacitors. At the instance of switching on, the capacitor is not charged and acts temporarily like a short circuit. The higher the capacitance, the higher is the amount of energy to charge the capacitor. Depending on the type, DC-DC converters can produce a certain amount of this energy at the instant of switching on. The maximum capacitance that is permissible to connect to a DC-DC converter can, as a rule, be found in the datasheet. Devices that have a negative internal resistance have an even more unfavorable effect and hence a relatively high current is drawn at low input voltage. Such behavior is shown, for example, by devices with an integrated boost converter, step-up converter, which belongs to the choke converter type. At the instant of switching on, every DC-DC converter initially has an output voltage of 0 volts. Over a period of a few 100 milliseconds, the output voltage then rises to the nominal voltage, for example, 9 volts. During the rise in voltage, the current required by the device may not exceed the maximum output current of the DC-DC converter to be selected, because otherwise the converter cannot achieve the maximum output voltage. With a laboratory power unit, it can be determined whether a device has a negative internal resistance. By gradually increasing the voltage up to the nominal voltage, it is possible to measure at which voltage the highest current flows. This value can be read either on the built-in current display of the laboratory power unit or on an external unit used to measure current, such as a digital multimeter. The DC-DC converter chosen must be able to deliver the highest determined value of current, which is needed by the device to be supplied, in order to ensure that the operating state is reached. However, this is only the case for startup currents, which are caused by electronic switches, and not startup peaks of capacitors. As a rule, the nominal operating condition is the most harmless case. The current consumption is below the maximum starting current, as well as below the operating state, where the most energy is required. The operating condition with maximum energy consumption can differ significantly from the nominal operating condition, for example, when an exceptional situation occurs in the application. This operating condition must also be taken into consideration when selecting the optimum DC-DC converter. The choice of converter must be able to continuously deliver the highest measured current of the device to be supplied, irrespective of the operating state where it occurs. After determining the output voltage and the output current, the power, P, of the sought-after DC converter can be calculated by using the formula P equals U times I, watts, where voltage, U, is measured in volts and current, I, is measured in amperes.